Good morning to everyone. I'm Dr. Karthikeyan. So I'll be talking about the analysis of synthetic polymers by GC and GCMS using this versatile pyrolysis technique. Okay. My talk outline, actually, I will briefly introduce the pyrolysis as a process, also the instrumentation for this pyrolysis GCMS. Then go a little further with the Py-GCMS working principles, also the furnace technology, what is out there and how we are different from the other technology. And also I would like to share some of the application for polymer analysis or failure analysis. Just I want to take a couple of minutes to talk about the Frontier Laboratories. Actually, Dr. Ramakrishnan has already done it, so I will not take much time here. So as he mentioned, we are actually into our 30th year, and it is located in Koriyama, which is actually part of the Fukushima prefecture. From Tokyo, it's about 1 hour travel by Shinkansen train. So the company size is not big, so 60 permanent employees and another 20 over contract employees. So by size, we call ourselves small, but the contribution that we made into this technology is substantial. So we call ourselves a small giant company. Okay. We have three major products as part of our company. One is the multi-shot pyrolyzer, which I will be sharing more today. Then we have another one called tandem microreactor. So that can be used for biomass research or the catalyst screening, excuse me. Then we have the third product that's a unique product of this metal alloy capillary column, so which I will be sharing a bit of it today. Okay, as the topic is polymer analysis, so just want to touch upon the basics. So polymer, as you all know, it is a macromolecule, so it's a large molecule which has repeating units of a monomer. So the molecular weight and the characterization define the property of this polymer. This is why people have to use a different type of analytical tools to characterize this material to define its application for different industries. In general, the pattern diagram of a typical polymer will have a polymer as a major compound, and in addition it will have additive and inorganics, as you can see here. Okay, so if you look at this additives, polymer and inorganic, so the polymer is holding the major portion of this entire material, and where we have to look at some of the thermal based analytical technique to characterize this type of polymer. So I will not talk about pyrolysis immediately, but I just want to say that thermal analytical technique is largely used for analyzing a polymer for different characterization. This slide basically talking about that. So information from polymeric material by heating. As you know, most of the people must be familiar with the thermogravimetric analysis that gives a kind of the temperature profile of the material based on the weight loss information. Then you have the enthalpy change that can be done by this DTA and DSC. Then mechanical change, because the mechanical property is also important to again define the material application for different industry. Then the evolved gases, basically that is where I'll be putting our technique, that the Py-GCMS or even the thermal desorption or even the photocatalytic degradation. So all comes under this evolved gas analysis. That means when you give a heat treatment or even photo radiation, the chemicals that are evolved or released from the material will be characterized by mass spectrometry or GC or GCMS. So in today's talk, we'll be talking more about the GC-GCMS part. Okay, just for the benefit of some audience who may not have heard about pyrolysis previously, so I just want to spend a couple of minutes. So pyrolysis is a process of like thermal decomposition of organic material at elevated temperature in the absence of oxygen. That's key, you know. So it's an endothermic reaction. So that involves a chemical change of chemical composition as well as a physical change also is possible. And most importantly, this process is irreversible. So the pyrolysis is a Greek word. So pyro means fire and lysis means basically separate. So you are firing a material, like you apply heat to a material to separate the chemicals from that material. So separating chemicals through thermal cracking is what the pyrolysis means. So here another slides just explain that. So just to compare what we know in our day-to-day life. So combustion. So even if you want to fire a wood in presence of air. So it's more called like a combustion, where it leads to complete mineralization of like converting all organic into a CO2 and only little residue like a char, which can be because of the inorganic and some of the high temperature organic. On the other hand, if you talk about pyrolysis, this is actually done in the absence of air or oxygen. So that means you are able to collect some useful products out of this process. That is actually char or bio oil or even the syngas. Okay, so under this, so then pyrolysis is actually classified as a two different area for research or studies purpose. One is called applied pyrolysis, another one is analytical pyrolysis. The talk today is focusing on analytical pyrolysis. However, I just want to spend a minute on this applied pyrolysis. I think many of you may be heard or at least known about this biofuel, okay, that is being produced from feedstock or any biomass waste. So basically what happens, so they take this biomass, put into a pyrolysis reactor they call it, and they apply a heat, so they can end up seeing three different type of products. One is the char, one is the biofuel, and also the syngas. So here people also use a second step process using certain type of catalyst, and that can really bring some value added fine chemicals out of this pyrolysis process. So the entire kind of studies is falling under this applied pyrolysis. So we have this tandem microreactor that can be used for optimizing the pyrolysis process as well as optimizing the choice of catalysts. But today we will not spend much time on that, but at least I want to say that applied pyrolysis is a process where again we can play a role to really enhance your productivity or even some of the innovations. Okay, let us jump into the topic for today. So the pyrolysis of polymeric material. Okay, so here again, going back to the combustion and pyrolysis. So if you take a molecule, organic molecule, for example, butane, if you apply heat energy, okay, in presence of air, then as I said before, it goes to the complete mineralization of carbon dioxide and water. On the other hand, if you do it under inert atmosphere, it can be helium or it can be nitrogen. So what happens, you are able to see the smaller molecules that are being like breaking down from the larger molecule. So here that the bottom example is shown for the polymer. So if, for example, if you are taking polyethylene, so same way if you apply heat energy, then you are able to really break down the long polymer chain into small hydrocarbons. Okay, this is what you will see in analytical pyrolysis. So when you apply a pyrolysis as a tool for analysis, and you are able to characterize a material, and it can also be used for the applied pyrolysis where the catalyst choice and pyrolysis condition. So here there's a small diagram again. So you see this as a kind of small reactor or chamber that has a in and out. So in this in, you can have a nitrogen or helium. Basically, we want some inert gas. And when you apply heat, so this material really break down. So with the help of this carrier gas, you can push it out. And if you connect that to one of the instruments like FTIR or MS or GCMS, then basically you are able to see the changes that's happening during the process or after the process. So one can call this analytical pyrolysis as a reactor for online monitoring, as well as you can do the characterization of the material by applying a heat treatment at different conditions. So here today we will be talking about this pyrolyzer with GCMS. Okay. Now we move on to that workflow because many of you may be familiar with GC and GCMS. In GC, you can introduce sample in 6 different ways. The most common one is the gas sample. You can inject, normally gas samples are injected in milliliters. Then go to liquid samples that are injected in microliter. Then people use something like a headspace. So where again it's a large volume, but you are not introducing the sample directly. You are collecting the gas that is generated in the headspace by applying some heat and other changes. Then you also have thermal desorption. Again, thermal desorption, you apply some heat, but you are not totally decomposing the material. And you have this PME, solid phase micro extraction. That's another way people introduce some of the semi-volatile compounds from water or air samples. And you also have purge and trap. So that means you have this kind of trap 10x, that can be used for capturing volatiles. Then that can be, so again, water samples cannot be analyzed by GC. So people use this Pageant and trap as a tool. So the last one is the pyrolysis. So that is what today I'll be talking. So what you see here sitting on top of the GC is more like you can assume first as a sampling tool. So that means you are taking a polymer into this furnace and you apply heat, okay, under controlled environment. So any compounds that are released or like because of the temperature change or even the breakdown of the compound, these compounds are qualitatively and quantitatively transferred to the analytical column. So that leads the separation. And finally, you use a detector as appropriate as required as per your objective. So MS or even FID. Okay, so that is a simple workflow. So you have a sample introduction on top of the GC, then that the volatiles formed or released from the material is transferred to a GC column for separation. Then you have a detector like FID or MS. Then you see this how it is being done. So since it is a solid analysis, so you don't need any sample preparation. You take a representative sample, but here we don't need a large quantity also. Generally it is in microgram or less than 1 milligram sample size. So we have a sample cup, because later I will explain why we need a sample cup. So you drop this sample cup into the furnace. Okay, so what happens? So this is actually, you leave the sample cup in the cold zone. So this is actually the heat zone, like where you preset the temperature of your analytical condition. So when you start the analysis, so this cup from the cold zone going to the furnace, okay, that means it's being exposed to the high temperature instantaneously. Then what happens? It leads to pyrolysis or even thermal desorption, depending upon the temperature you set. Then so many compounds are being released, and with the help of the carrier gas, they are pushed through to the column, and this is where the separation happening. Then finally you see output something like this. So that can be because of the different compounds present in this material. So here this is an example for phthalate, because as you know, phthalate is like now that the controlled chemical. So electronic industry has to ensure that they do not use a lot of phthalates in their plastic. So that is a kind of a regulation now under RoHS. So the phthalate concentration should not exceed 1000 ppm. So this is one of the application, but this one falls under thermal desorption, because you are not totally doing the pyrolysis, because the phthalate is a volatile, so it's additive. So you just have to do only thermal desorption. So when you do pyrolysis of a polyethylene, for example, at 600 degree, you get a chromatogram, something like this, which we call it pyrogram, because the process is pyrolysis. So you get a, so here two things I just wanted to highlight. One is you can go even to see the peak for C100. So any large molecule, we don't have any kind of limitation. So you can really get the information as much as possible with this. Okay, so as you know, you are getting a chromatogram with multiple peaks, then the peak identification is another challenge, which we'll talk about it. So if you look at this, there are another different type of pyrograms or chromatogram that is for different type of polymer like polyethylene, polypropylene, polystyrene, or methyl acrylate copolymer. So what it shows that you have a kind of fingerprint or template for different type of polymer that can be used for identification of the polymer, synthetic polymer analysis. Now the question comes, okay, these all clean chromatogram or pyrogram when they are as a single polymer. So if I have a sample with multiple polymer, are we able to do it? The answer is yes. You can really get the data interpretation even for mixed polymer. So this is where you have to choose the right technique. For example, if you are using FID, then the compound identification mostly done by the retention time of the different compounds. But if you use a mass spectrometer, then you have more information. So in some case, even if you have two compounds are being co-eluted, with the help of mass spectrometry data, you can still separate these two depending upon the information that you have got in hand. So there are two ways that data interpretation can be handy. If you are using a FID, we recommend there is a good handbook for this Py-GCMS data, where you also have the data for FID as well. So with the help of this, one can always do some of the unknown analysis if you are using a GCFID. But as you know, if you have MS, you have more information. And one thing we have to say here, even if you have MS, if you are using a NIST library, then you cannot get all information that is coming out of your polymer. The reason NIST library is built based on the liquid injection. So where you know the temperature cannot go beyond like 300. So for polymer, you need higher temperature. So the NIST library do not have the database for polymer. That's why we have a kind of database, which I will talk about it later. Now I'm coming to the topic that we will deep further, like dive further. Basically, the Py-GCMS can help you to look at the identification of polymeric material. If somebody is giving you unknown plastic or unknown polymer, and you can tell them whether this is a polypropylene or PVC or even some type of rubber. The polymer, this Py-GCMS application can be used for structural characterization. That means the unchained compound can be looked, and also if it has a different monomers that can be easily identified. Even the stereo regularity, so some of the stereochemical analysis also can be possible with this. But today I will not go into that application, but I just wanted to say this is possible. So mechanism and kinetics of polymer degradation, either it is a thermal degradation or photocatalytic degradation, can be possible. Even you can look at the equilibrium, because as I said before, this pyrolysis system is seen as a micro reactor, because anything you do in the reactor, the output is connected to a GCMS. So you are collecting the information that can be used for your reaction mechanism. So this technique can be used for qualitative as well as quantitative. Now let me take 5 minutes to introduce the instrumentation and technology of this Frontier Pyrolyzer system. So this is how it looks like. So in previous slide you would have seen this is more like a micro furnace with some, and this is a processor. So with the help of, it's like a CPU, you can call it, for computer. So many things what we want to adjust or manipulate is processed through these processors. Okay, and we have two products. One is called single shot, another one is the double shot or multi shot. So the single shot is more like a flash pyrolysis. That means at any given time you can only set one temperature. It is meant for only isothermal. So if you are interested only in polymer analysis, so single shot. But if you want to do more kind of research or unknown or failure analysis, then one has to consider choosing a double shot analysis. Because what is the main difference between this single shot and double shot? The double shot can be classified as a multi shot also. Basically, you are able to change the temperature condition as a programmed manner. Okay, so you can do the ramp up change, you can do the settings for increasing the temperature in different rates, like 10 degree per minute or 20 degree per minute, or you can also hold in certain temperature for certain period before you continue the second step heating or so. So that is the feature of the double shot. So many R&D people or the people who are working on reverse engineering or failure analysis prefer to have a double shot or the multi shot. So the main point here, you just have to assume that this is just a sampling tool that is sitting on top of a GC, and with the help of the processor, the furnace operation condition can be easily manipulated as we prefer. The pyrolysis system is not a standalone system, so that's also important point you need to understand. So if you buy only the pyrolyzer, you cannot do anything. So because the information has to be gathered by something else, so it has to be coupled with a GC or GCMS. And here we just want to highlight this system is compatible with all major brands of GC, whether it is Agilent or it is Smatso or it is Thermo. So it is just sitting on any of this GC, then the compatibility for all major manufacturers is there. Okay, so that's one important message also you have to. Two things. One is the PY system is not a standalone system. It has to be combined with a GC, and it can be combined with any brand of GC. Okay, now I just want to spend a couple of minutes to talk about the technology that where we can differentiate our technology against other competitors or like other technology. So there are three type of furnace available in the market. Okay, the one is actually called a filament pyrolyzer. Okay, another one is called Curie-point, and third one is the micro furnace that is coming from the Frontier. So in this filament pyrolyzer, so they are using a filament, so they apply the pulse mode heating. Okay, and so that means you only generate heat by this filament, and there is a quartz tube, and your sample is put inside this. So that means whatever the temperature you are setting for the filament does not need to be the same for your sample. So that is one major difference. And secondly, this instrumentation has got a lot of valves and a lot of transfer lines. Okay, so that's another limitation, because if you have longer transfer line, it can easily create some cold spot, because you are doing high temperature treatment, then it is going through a transfer line. If the temperature is not properly maintained, it can create a lot of cold spots, so you end up losing some of the compounds and you end up facing the carryover problems. So the second technology is Curie-point pyrolyzer. Basically, they have a kind of foil. Okay, that means different alloy foil in which they add the sample, and it can really enhance your fast heating. But the temperature setting is something you cannot prefer, because it's based on the type of foil you are using. Because here basically done by this ferromagnetic foil, there are different foil available for different type of temperature that you want to achieve. So that's a limitation here. That means that the limiting factor is the type of foil you have to use. So something, if you want to try different, it's not possible with this Curie-point. But this is also a vertical furnace. Now moving on to the Frontier Lab technology, which is actually a micro furnace, again a vertical furnace. Okay, so vertical furnace, basically you have a ceramic tube or stainless steel tube, and here the furnace gives the precise temperature for the sample. So that is something that we have done. So later I will explain that. So that is one key difference compared to other technology. So you are able to apply the same temperature or the set temperature to the sample. That is key. And secondly, it is just connected on top of the GC transfer line, so there is no other extra tubings or valves, so you have less chance to create any cold spot. And thirdly, you have this sample standing position. That means this is a cold zone. Okay, so that means you are not exposing any heat before your analysis start. Whereas in this case and this case, you have to keep the sample first, then you start the analysis. So that means during the process of heating, your sample is already inside. So that means the reaction is already starting before it attains its desired temperature. Same case for this Curie-point also. Whereas in this case, you set the temperature, then you drop the sample. So immediately it is being exposed to one desired temperature. Okay, so that is what you will see in the next slide. When you use the pulse mode, okay, basically, as I said, the sample is kept and the heating is done slowly. So during this heating process, you already see some reaction happening. That can be evaporation, that can be denaturization, or even some degradation or thermosetting like a curing. So that means some of the information you may lose, or it may be coming in the next sample analysis. On the other hand, the Frontier technology uses a continuous mode, so you maintain the sample in ambient temperature when it is held at the top. The moment you start analysis, then it is being exposed. So the sample reach or receive the temperature of this high temperature within 20 milliseconds. So that means that the pyrolysis is generally a spontaneous one, and that can be accomplished much easier in this technique compared to the pulse mode or ferromagnetic coil. So this is a unique technology difference that Frontier offers compared to other technology available. So that is on the technology part. So on the analytical technique part, because we have shown like two kind of product. One is the single shot. Single shot, you don't have much option. So you basically just set one temperature in you analyze. It's more like a flash pyrolysis. But the double shot or the multi shot, you have more things to explore. Okay, that is what we call it. So we always start with something called evolved gas analysis. The evolved gas analysis basically tell you the compound nature, also the temperature profile, based on which you will decide whether you want to do the pyrolysis directly to get the information, or you can also go for two-step analysis. The first step, you get to do the additives by thermal desorption, and the same sample you can do for pyrolysis for the polymer. And you can also do something called hot cut, EGA followed by hot cut. That means the temperature zone of the evolved gas analysis can be like directed to GC for multiple analysis. So you can get 5 different analysis from one sample by treating the sample at 5 different sample temperature as well as 5 different heating temperature. So that is where the hot cut. So later I have example to show. So you can also do something called reactive pyrolysis, because some of the polymer, okay, it's like a condensed polymer, they cannot really even get decomposed with normal pyrolysis temperature. So you have to really convert that with a kind of some methylation reaction. So either you can use methanol or tetramethyl ammonium hydroxide. So here, since it's already part of a heating, normally any other flame analysis, if you are doing for some oil or other compounds, free fatty acid analysis, you have to add this reagent and allow it for some reaction, then you do the analysis. But here it can be done together because it's already being exposed to the high temperature. So this reactive, the methylation reaction also being accelerated here. So it's going in one time. So you don't have, so we call it in situ reactive pyrolysis. Okay. So that are the different technique. So how we use this different technique is basically we start with the evolved gas analysis. So that gives information on the compound and temperature profile of the material. Then you decide whether you want to do thermal desorption or you want to do hot cut, you want to do pyrolysis, or in some cases you may have to add some reagent upfront during EGA process. Then you get the information even for that. So that is the way that you can easily map it. But all this you can do only when you get the EGA data, because without that the sample coming to you is as an unknown. So you do not have a lot of sample information or history. So this EGA really opening up the ideas to get more information or as much as information possible from a sample through this pyrolysis GCMS. Okay, this is again showing that. So you start with sample preparation is basically transferring a representative sample to a sample cup for the analysis. From the EGA data, you decide whether you want to do only single shot or double shot or hot cut. Then with the help of our library, you get more information. And yeah, some of the additives you can even use the NIST library, but for polymer, you have to consider getting a data book or the library that we have. So the workflow, again, it's very simple. So you have different type of polymer. It can be a block, it can be rubber. So you use knife or you use some kind of prepper. Or if it is a liquid polymer, you can use micro syringe. If it is a sheet, you can use a micro puncher. So the sample preparation is only taking a representative sample. Sample size, as I said before, doesn't have to be very large because GCMS is a sensitive technique and you don't need a large sample. And every sample, the compounds are being transferred, so you are not doing any pre-concentration or anything. So as it is good enough to get a good amount of like sensitive signal from each type of sample. So you place the sample in the sample cup, then transfer to the furnace. It's ready for analysis. Okay, now I would like to start about the method of 4 different analytical techniques or the method mapping. So I want to start with TGA because people out there may be known at least for TGA, but EGMS is something new for you. So let me start with what you people know. So TGA, as you know, is a kind of thermogravimetric analysis where you again take a sample of like 5 to 20 milligram, then you apply heat same way at different ramp rates. Then what happens, because it's an organic molecule, so it decomposes, so there is a weight loss. So it captures the weight loss information, and this is what you are seeing. So the weight loss information basically tell you at what temperature it is stable or what temperature it start really decomposing. Then the same data can be put into this DT, the differential thermometer is more like algorithm. Then you get the peak top temperature for additive group and polymer group. On the other hand, if you are using EGA, we are not collecting any weight loss information because we are collecting the compounds that are being released. Because here you are not collecting the released compound, you are only looking at the remaining, but here you are collecting the released compound. Okay, so that's a major difference. So anything coming out, and here in EGA, you have to take a note also, we are not using any analytical column, because analytical column, if you use that, also play a part in separating chemicals. Here we are doing a thermal separation. So that means we want to see at what temperature, what type of additives are present in this material and what type of polymers are present. So we get a kind of two major peak, okay, one for additive group, another for polymer group. Okay, so this peak is something similar to what you see from TGA also. Then what is the difference is, most importantly, this peak, when you, like if you are using MS, then you click on this peak, you have a lot of information from the mass spectrometry, the mass spectrum of different compounds. That is something not possible with the TGA. So that's a major difference. And these days, if you are doing some research, it is very difficult to publish your work with just TGA. You have to go with TGA, with MS, or some other like Py-GCMS separately. So here the point is, you can do EGMS and get all this information in one hand, and more information. Even this data can be used for deriving the the degradation kinetics. Okay, so the EGA is the first step. Then we have to use the chromatographic analysis for hard cut or single shot or double shot. So then the question comes, as I said before, we are not using any analytical column for EGA, but for the other techniques, you have to use analytical column. So that means you have to change from tube to column. If you are using MS, this some may feel is a headache. We have an accessory called a vent-free adapter. This vent-free adapter allows you to keep your mass spectrum or the vacuum without any kind of disturbance. You don't have to vent it. You just only dismantle the column from here and connect the new column. But during this transition, you can also put a cap here so that you ensure that you are not allowing any air getting into the mass spectrum. So this vent-free adapter really makes your life easier for changing column. There are customers who are buying this vent-free adapter even if they don't have pyrolyzer also, because in your laboratory, if you are using a different column for different analysis, and if you are using GCMS, so your downtime can be avoided, okay, if you are using a vent-free adapter. So here particularly we want to say that with the help of this vent-free adapter, doing these four techniques like EGA and single shot, double shot is not really a major challenge for us. So because changing of column is much easier and faster when you use vent-free adapter. Okay, so the major data output difference, if you are using EGA, so you get only few peaks because there is no separation through the column. So this one peak may have multiple compounds, because this peak represents the temperature characteristics of different compounds that are being evolved together. Okay, but at the same time, if you are using single shot or double shot, you have more number of peaks for the same sample, because it is going through a separation process in the GC column. So that is the major difference between EGA and Py-GCMS. Okay, so let me take through this four technique very quickly. So let me start with an example. This is actually a kind of eyeliner. Okay, eyeliner is a cosmetics that has a lot of water soluble polymer, also some solvents. So if they want to really characterize this to ensure that they are using because they do not want to see it's being evaporated very quickly, because then customer cannot use it. So it has to maintain certain level of evaporation period so that the customer buy and use it properly. Also the chemical they are using, they are not really toxic to the human. So this characterization require a technique like Py-GCMS. So when we do the eyeliner, it's very easy. The sample you just, because it's already kind of liquid, so you just scrap on the sample cup, then you do the analysis. So EGA, basically you start with a 40 degree and up to 500 or 600, 20 degree per minute. And this is what you are getting. As I said, you may not have too many peaks, but there are some peak humps. So when you have more peaks, you can say that you have mix of material that has different temperature characteristic, and also the compounds may be of different. So what information you are getting from EGA is basically how many peaks and what temperature. So based on that, you can set your next step. Okay. So if somebody do the flash pyrolysis directly without EGA, can it work? The answer is yes and no. Because for some samples, if it is not very complicated material, a single shot can give you the information that you are looking. Okay, but your sample is complex like a cosmetics, where you have solvent, you have additives, you have polymer, mixed polymer, then you have a lot of peaks. Then sometime you may have a coalition problem or so that's the problem that you may have to overcome. So single shot can work in few cases. In some cases it is preferred to do the double shot. So later I have application to show this difference. Okay, so double shot is the ideal approach for most of the analysis. What happens? So with the EGA data, you know what are the compounds that are being released before 300. So that can be set as your thermal desorption process. So 40 degree to 300 degree, 10 degree per minute or 20 degree. So 20 degree, 20 degree per minute is the kind of rate we use it. So whatever the compound they are being released during this thermal desorption from 400 to 310 is being sent to the column, then the separation starts. Okay, it's like a two-step. Whereas the pyrolysis is not a two-step, it's very fast. So you have a holding time of only 1 minute. Whereas in thermal desorption, your holding time can be 10 minutes or 15 minutes, depending upon the rate that you are using for your heating. So that's one big difference that you have to understand. So, but this is a very common approach for any type of sample. You try to collect all additives or other like kind of agents in the polymer with the thermal desorption approach, then pyrolysis for the polymer. So here, because you have only one peak, it's because it contains only one polymer. If you have multiple polymer, later I will show that, then you may have more peaks coming in the pyrolysis also. So when you have more peaks in pyrolysis, more peaks in thermal desorption, if you are doing a single shot, all these peaks come together may give you some kind of challenge for your data interpretation. So the fourth one is the hard cut. So the first one is EGA, evolved gas analysis. Second one is single shot. The third one is the double shot. Now fourth one is hard cut. Hard cut is basically is more like a two-dimensional GC, which you would have seen before or at least heard about it. So when you have multiple peaks coming from your first column, then each peak you can divert into the second column for further separation. Okay, exactly what is happening here, but here the first step of separation is done by the heating. Okay, then the second step of separation is done by the column. So that's why we call it hot cut. But the first is not GC, it's a EGA GC. The first separation is done by a thermal treatment. So here if you look at 1 2 3 4 5, so you can get 5 different chromatogram of a same sample by doing this hard cut analysis. So what happened when you do these 5? For example, this sample is a kind of cosmetic. So you need to have some moisturizing agent because so that will come always in the first zone. Then you have some of the preservative just to ensure that the cosmetic can be used for a certain period of time. Then also some of the skincare material. So different zone information can be separated or like obtained with a multiple chromatographic run, and that is required for certain complex analysis or reverse engineering or failure analysis. So I have two applications to show how the failure analysis is handy when you use the EGA hard cut. Okay. So as I said before, two things have to be keep in mind. So it is always good to have this data book because this has a data for 1000 more polymer. So it's always like a Bible for you to look back some of the standard chromatogram for different polymer, and that can be useful for interpreting your sample analysis or the sample data. And second help is coming from us that we have something unique software that is F-Search. This has 4 different databases. One is for the EGA, one is for the additive, another one is for the Py-GCMS combination, and also the pyrolysis. Pyrolysis is what? The different peaks, okay, that is coming out of the pyrolysis. Each peak is called a pyrolysis. Whereas this one is called a combination of, because one polymer may have 40 peaks, another polymer may have only 30 peaks. So this one, instead of looking at each peak separately, you combine all peaks. It's like a summation of peaks for each type of polymer. Then you do the integrated summated mass spectra based on which the algorithm is used here. So we have a database for this summation of peaks for 1000 over polymers, because the pyrolysis type of interpretation is not very common that you require. You can do your data interpretation with these 3 databases, EGA, additive, but only for some cases you have to look at the individual peak. So we have this database also for some tough polymer. Okay, but most of your polymer analysis interpretation can be done with these three database. So this is F search. Okay, this is something available only with Frontier Laboratory. Okay, now I have talked about the technique in terms of the technology, in terms of the method mapping or analytical techniques, where we discuss about EGA, then single shot, a double shot. So the first application I'm showing it here is basically a single shot analysis of an unknown resin. So this resin has got a multiple polymer. Okay, so the customer is interested to know what type of polymer they are. So they are not really keen to know about the additives part. So then we recommend, okay, single shot is good. So when we do the single shot, it's basically a flash pyrolysis at 600 degree. So you have multiple peaks. So with the help of our F search, you are able to look at the pyrolysis of different polymer. So we are able to tell, okay, this resin has got three type of polymer, PMMA, then Py-GCMS and polystyrene PS. So this is the main benefit of Py-GCMS. You are able to do a single polymer or mixed polymer, okay, by flash pyrolysis. Now let me show another example. This is an example for unknown black rubber. As you know, this rubber is used in tire industry, in other industries, and where they have to use the different additives like accelerator, anti-degradant, and also the antioxidant plasticizer. Okay, so definitely the competitors always look for the best choice of these compounds to have a super performance. So this customer basically wanted to analyze all these additive compounds and the type of polymer present in this. In this case, we prefer to do a double shot. As I said before, we start with EGA, but EGA data I'm not showing here. From the EGA data, I know my all these volatile compounds can come before 320. So we do the thermal desorption program from 100 to 320 degree, and we have all these compounds being separated with the help of the GC and MS data. Then with the help of our library, we are able to tell what are the different plasticizer. It's basically the phthalate, and you have this trade name for this antioxidant, for anti-degradant, and also the accelerator. Okay, so this information something is very difficult to get from other libraries library. So that's why we feel that the FSS library also will be handy when you are getting analysis done by this PY or thermal desorption GCMS, particularly for polymeric material. Okay, so the second step, we do the pyrolysis. So in this case, based on the EGA, we set the temperature as 550, and you have basically this consists only one type of polymer, that is isoprene. So the second example I have shown is actually using a double shot, where the first shot, the thermal desorption, is used to collect the information on the additive compounds. Then the second pyrolysis step is to look at the polymer type. Okay, so that's the second application. So this is what basically the customer wanted to know, what type of polymer this rubber has and what are the different additives that I have in this rubber. Okay, and based on that they can really define their application, or if it is a competitor material, they can choose something equivalent to really develop their new material. Okay, so this is another just example to add. Even if you are talking about a blend of rubber, okay, that is possible even to the quantification level, because so you can do, definitely I told you before, the mixed polymer analysis is very easy with the Py-GCMS, but even quantification, but for quantification you have to really create some calibration graph for each type of polymer with a different composition. Then when you do the unknown analysis, you can easily tell, okay, what kind of butadiene present in this or isoprene. So you have to create such composition calibration graph for three different compounds separately, based on which you can always find or the analysis of blend polymer as an unknown sample. Okay, now I have two more applications to show how the failure analysis will be handled with the Py-GCMS. So here the first example, we have a customer who actually use same facility for manufacturing different polymers. So here they use, one is actually the polyvinyl alcohol, another one is the ethyl vinyl acetate. So suddenly they find that their final product is not qualified because it has higher turbidity, but they don't have any flow. So they brought the sample to us. So first we did the simple flash pyrolysis single shot. You can see the good product and the bad product. We cannot really tell much story from this. So that is what I said. Some sample, if you do single shot, the information what you are looking cannot be obtained. So then you have to go for a systematic approach. So that means that start with the EGA. Okay, when you do the EGA, you are getting the comparing the good one and also the failed one. So you can see there is a difference in this second zone here. So that means some compounds are here that is not there in the standard. So there are some extra compound. So that could be a reason for this turbidity, which we do not know. So we try to get some mass spectrum from this, but definitely that information is not sufficient. So it can only tell there are some contamination in the failed product. So the best way to get more information about this different is go for hot cut. So that means instead of getting the separation of entire polymer, the PVA, we only analyze this portion 460 degree to 540 degree. That means we have the selective sampler that can help you to send the preferred zone. Okay, that means rest will be always vented. Okay, so it will go as a vent. So that means if you are doing hard cut analysis, you have to have this accessory. Otherwise, it's not possible. For single shot, you don't use this accessory. Hard cut, you need to have this. Okay. So what we are doing, instead of doing multi-shot, we just, because our interest is only to look what is the difference here. So we only do the hard cut analysis of this fraction. Okay. So what we see here, there is actually some kind of this unsaturated hydrocarbon peaks that are coming at this 57. That is not seen in the good product. Okay, then we need to understand what is the problem. Okay, so that is, we cannot tell this part. Okay, so we have to go back to the customer. Okay, we find something extra in this turbid polyvinyl alcohol compared to, so that is basically, sorry, so it's actually saturated hydrocarbon. So with the 57, so this saturated hydrocarbon, then they know why it is coming, because the same facility previously they have used for ethylene vinyl acetate copolymer manufacturing. So after that manufacturing, usually they have a cleaning process in place, but they do not have a QC to ensure that the cleaning is done fully. So because of some EVA leftover, it affected their manufacturing of the next batch of this polyvinyl alcohol. So then the question comes, can we really quantify? So we did some PVA analysis of different concentrations to establish a kind of calibration, and we found the turbid compound has around 1000 ppm of this EVA. So that means if they are doing a cleaning, the cleaning water or cleaning sample should be analyzed for PVA content to ensure that it is below 1000. So this is how we help to sort out the failure analysis. So that's okay. The second application is more like a reverse engineering. This is for the coating, automotive coating. So coating material has got, like, there are two kinds, inorganic coating and organic coating. So here our interest is only in the organic. So polymer and wax. So within polymer, it can have silicone, acrylic resin, fluoresin, and urethane resin. So this particular customer wanted to know what kind of urethane resin they are using and what is the different composition. So basically they bring two samples. One is their own product or one is their competitor product, but we don't know. The idea is they want to see what is the major difference between these two compounds. So as I said before, we always start, because our starting point is EGA. So EGA tells you how many hot cut you have to do it. In this case, actually 1, 2, 3 is enough, but still, to be on safer side, to minimize our repeat analysis, because it's a reverse engineering, means you have to do a more detailed analysis. So we have separated into 1, 2, 3, 4 zone. Okay, so the first two zones for additive evaporation, and the next two is for polymer. So we do the hot cut analysis in this case also. So both samples are being compared. So I will go to the summary directly, because basically it just tells a different type of polymer and additive present in this. So because of the time, I cannot discuss those details. But the most important point that I want to highlight here is, so when you compare this, so what is the compound that you have? So most cases you found some of the compounds are present in both sample, but some compounds are present in one, not in the other one. And third difference is some compounds are present in both, but the concentration is different. So that is the summary. So which I should run it up. So here, because earlier I was showing the chromatogram for 4 different zone. Okay, to summarize what was the major finding. Okay, in first case, this PHT was found in both sample, but one has less and other has more. And this, because we are not a coating expert, so we do not know what causes this low or high, because they know the application aspect. So for us, only giving the information which material has got a less or more. That's more like analytical information, that the characteristic of the material that they wanted to analyze. So what you have to see here, as I said before, some of the compounds are present in both, but the concentrations are different. So this customer may want to optimize their concentration to really match with their competitive material. And they also found some compound that is present in one material and that is not present. For example, isobutanol present in one material, sample A, but it does not have in sample B. Similarly, the one butanol was not present in sample A, but it was present. So these are the difference. So this information will be very handy for them for this research, the method development or the material development group to really take their next step. So this is another example. So Frontier Lab has come up with this unique ultra alloy capillary column, metal capillary column. And definitely the people who are using other fused silica column, capillary column, may know the limitations in terms of handling mainly. Okay, that is one thing. And second is actually the temperature, also the temperature tolerance, high temperature analytical condition. That is something is but there are some new product coming in fused silica also where they can go to high temperature, but the kind of the rigidness what you can see the metal cap, because by a layman per se also one can say okay, metal capillary is more rigid than the fused silica. As long as you are able to get same performance, definitely as a user you want to have a metal capillary column. So this is the historical development of the capillary column, which I will not spend much time. So here our capillary column, basically we have this two different diameter, also 0.1 and 0.25, and we have multi-layer coating. Okay, so this is the SEM data of before and after, and our tube also being deactivated. Okay, so we have some major difference in this case. First, we don't have any external coating like a polyamide that is required for the fused silica. So we are able to go high temperature, okay, from that material, the column material per se. Then we can do a kind of more times, because we have put 4 times, but at least we can say 3 to 4 times. So the lifespan of the column is, that means our coating is more stable, so you can do more analysis with our column. And third important benefit is thermal stress, because if you are really looking for some very volatile compounds, so if you are using a cryo trap,
Karthik, when
yeah,
I see in the number two, it is longer lifetime because
yeah,
people I
that's
don't
correct.
want them to get confused.
Yeah, that's correct. This is a lifespan. Yeah. Yeah, it's actually so the file is wrongly put. It is a lifetime. Yes, that's correct. Yeah. So the thermal stress, basically, yeah, because if you are doing some cryotrap analysis, the column is being exposed to very high temperature, and low temperature means it can go to minus 100, minus 200. So that also can really rupture the column. So this is the metal capillary can take such a thermal stress. Later I have a slide. And fourth one is the mechanical strength, like it's a capillary, metal capillary, so you don't have to be really very cautious compared to fused silica. So it can give a very good data, even as I said here, the example with the 0.1 micron, like a film thickness, micrometer film thickness, for two type of like a very complex material like polywax and motor oil. So you can get very good separation, what you may not be able to see with the fused silica. Okay, and as I said before, the cryo trap. Okay, so this column is being exposed to very low temperature, then it's again raise the temperature for the analysis. So this kind of temperature shock ultra alloy can take. So whereas the fused silica can break in 2 days or after 8 times. So that's kind of number that based on our own studies. So as I said before, you can see that the column performance or the separation or the peak pattern is being deteriorated after more number of injections. So here for the ultra alloy, initial injection and after 80 injections. So here initial injection, after 20 injections. So you can see already there are some kind of tailing issues coming even after 20 issues. So based on this only we say up to 4 times, okay. But it is another time, another, so here if you look at it is like a 2 to 2.5 times. So we do not, because this is very subjective what type of analysis you are doing, but one definitely is a kind of a benefit is it has longer lifetime, okay. So that's a key thing, but the lifespan can be 2 to 4 times. In some case it may be 2, some it can be 3, in some cases it is depending upon how you handle it and what type of analysis or what type of samples you are doing it. Okay, so with that, I would like to sum up my talk, what I have shared so far. So the multimode pyrolyzer with GCMS, okay, it's just a powerful tool for material characterization. That's for apart from a QC analysis, for unknown sample, failure analysis, and reverse engineering. And EGA, sorry, it's a again typo, EGA-MS, okay, the hard cut. The EGA-MS and hard cut GCMS makes it unique, okay, for the Py-GCMS application, because if you do only single shot, you do not have a lot of information, okay. So the advantage of Py-GCMS is the direct analysis. That means every chemist in the laboratory like to have that. If you are able to analyze any sample directly, that's the best option they want to choose, and that is something possible with Py-GCMS. And as I explained briefly, the ultra-alloy metal capillary column has got distinct advantage over traditional capillary column in terms of the durability, high temperature tolerance, and mechanical strength. So with that, I would like to thank